Hello, Mr. Ryan. Are you right? Yeah, we haven't done coding for a while because we're on holiday, right? And today is the 700 day. Good job, yes. Okay, so by looking at this, can you remember what we talked about like a few lessons ago? Look at this. When n equals 3, we given an integer n, we want to return this. When n equals 2, return this. n equals 1, return this. So what are these?
What combinations you can make?
A few lessons ago, we talked about generate the binary string without the adjacent zeros, right? So we don't want two consecutive zeros. Do you remember? Look at these strings in comment, right? Okay. So on that day, what algorithm did we use to solve this problem, to generate the binary string without the consecutive zeros? Okay, we want to generate a binary string, binary 0 and 1, right? Without consecutive zeros. So basically, we don't want the two zeros in a row. Ryan, I think last lesson you mentioned about brute force. So the idea of brute force is basically generate all the combination, all the binary strings, and then remove those with double zeros, right? At least double zeros. So that will work, right? For example, if we are given this n is the size of the string, so that would be altogether that would be 2 to the power of n, right? Because each digit there are two choices. So 2 times 2 times 2 times 2. If you multiply 2 n times, that gives you 2 to the power of n. That's the total number of all the strings, binary strings. And then for each string, we just check if it consists of these two zeros, okay? Does it make sense? So the idea, the overall time complexity is O 2 to the power n times n, right? Because for each string, we have to check if there are two consecutive zeros, and that will take another additional O(n) time, right? Right? Yeah? So depth first search, right? Last lesson, we talked about the depth first search to solve this problem. Okay, depth first search. So how do we solve this in depth first search? Basically, look at this n, right? So the idea is that, we start with the empty node here, empty string, okay? So the first choice is we can obviously put a 0 or we can put a 1, right? If the last digit is 1, we can put 2, we can put 1, and we can put 0, okay? But if it's 0, we can only put 1, right? Yeah? So it's kind of like binary tree, right? But instead of generating all the strings, we don't generate the invalid strings, because there's no point to generate 0 here, because they will contain these two consecutive 0. Alright? Yeah, does it make sense? So this is kind of like binary tree. So we basically check, right? We just, we just implement the depth search using recursion by traveling the binary tree. If the previous node, right? If the previous node is 0, then we can only generate the 1, right? We can't put the 0. But if the previous is 1, we can put either 0, or 1, right? We can put both 0 or 1. Am I right?
Yeah.
Yeah. So this is depth first search.
Breadth first search.
Breadth first search. Do not breadth first, okay? You eat too much breadth first these days, okay? Breadth first search. So what's breadth first search? So can you tell me, what's the difference between depth first search and breadth first search?
Breadth first search is when you breathe in a straight line.
Okay, so look, let me give you a...
It's level by level.
Okay, so let me give you a binary tree.
No, Q.
What do you mean, no?
It's Q.
Okay, so this is the binary tree or whatever, right? The depth first search, breadth first search are both the graph traversal algorithm, right? Meaning that, we can use it, we can traverse the graph, right? Using these two approaches. So a binary tree is a graph. N-array tree is also a graph. It doesn't have to be binary tree. It can be a graph, right? Graph is the data structure with the nodes, with the vertex and edges, okay? And it can be how many types of graphs?
Lots.
Lots, like directed graph, undirected graph, right? Weighted graph, unweighted graph, and a combination, right? So it could be weighted, directed, or weighted, undirected. And DAG, what's DAG?
Directed analog graph.
Directed acyclic graph. It means that it does not have cycles, right? Okay. So what's cycle? Look, this one is cycle.
No.
What do you mean you know? This is the cycle, right? This is the cycle. A simple graph, complex graph. We talk about it lots of times. So breakfast search, the order 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. The depth search, different orders, with different traversal orders, right? We could have a pre-order, post-order, in order. Okay. So let's talk about the depth search, recursive depth search. So we visit the left tree as deep as we can. So what's the order of depth search? If we visit the left trees first, come on. Can you get this right?
1, 2,
1,
3, 4,
2,
5, 6, 7, 8, 9.
No, that's breakfast search. What's
1,
the?
2, 4, 5, 3, 6, 8, 9, 7.
Okay, you got it. Okay, so let's implement the breakfast search. Okay, what do we use to implement the breakfast search?
Huh?
What's the data structure we use to implement breakfast search? How do we
Q.
implement Q? Yes. What's the data
Stack.
structure? Yeah. Okay. Yeah, you got that. Right? Define. Name the function, Ryan.
No.
Breakfast.
Sorry.
Breakfast.
BFS. Okay. So let's say we
No,
give an n.
breakfast.
Breakfast. Okay. N. Given an n. Right. Of course, we need to make sure this n is bigger than 0. Okay. If it's 0, then we return nothing actually. Okay. So Q, DQ, double NDQ. So at the beginning we return. It contains an empty list. Okay, look at this double square bracket. So the inner is the empty list. Okay, then answer, we put the answer here. While there's element in the queue, then we get the front of the queue, right? We get the front of queue. First in, first out, right? So here we have this element, right? So the current equals q dot pop, which side? Which side? Pop what?
Pop left.
Pop left. Why?
Yeah.
You're scratching your back.
That's
Okay. So now, so if so what do we do? If the length of the current is empty, right? If it's empty and the beginning is empty, or what? Or the previous element is 1. Is 1, right? If it's empty or it's 1, meaning we can put a 0 in, right? So we put a 0. Q dot append current plus 0. Okay? And then in both cases we can put a 1, right? We can always put a 1, am I right? Yes, we can always put a 1. So Q dot append current plus 1. Okay, this needs to be in a list. So this is the list. We concatenate the list by another list. Okay, now we have to check, right? We get this current, now we have to check if the length of the current equals n, then we need to put it into the answer, right? Answer dot append empty dot join this current, right? Yeah? And then return what? What do we return? What should we return at the end? What should we return? Answer, of course, return answer is there, okay? So, look, here, let me explain this one more time, okay? And then let it be.
yes. Let's go.
Come on, line by line, okay? Q, we using the Q to implement the breakfast search. And at the beginning, we put the empty list, right? This is the start of the node. Empty list, okay? And then, if it's empty, then we can put either, 0 or 1, right? If it's 0, we can only put 1. But if it's 1, we can put both, right? We can put 1, 0 or 1, 1, right? Yeah? So basically, this is the same thing, right? If the previous node is 0, we can only put we can only append the 1. If it's 1, the previous character is 1, we can put either 0 or 1, right? Okay, and then, why there's element in the queue? We first get the element out of the queue. So, from the left hand side, right, first in, first out. Then we check if it's size n, then we get it one more string, then we put it into the answer. Otherwise, right, if this is to append the node into the queue, back to the queue, and then we repeat this process until the queue is empty, okay? Okay, that's it for today, bye-bye! Bye-bye!